this video, we're going to learn about magnetometers. Magnetometers measure magnetic fields along one or more axes. With the magnetometer, you can turn your Arduino into a digital compass. In this video, we're going to make a digital compass and print the sensor's heading in degrees and its cardinal direction to the serial monitor.
Before we get into setting up magnetometers, there's something I have to warn you about. Magnetometers are usually pretty easy to set up, but I ran into some trouble at first. The most documented magnetometer for the Arduino is the HMC 5883L. So I found one on eBay and I ordered it. But no matter what I tried, I couldn't get it to work. Then I discovered that even though my magnetometer was labeled as an HMC 5883L, it was actually a QMC 5883L. Libraries written for the HMC 5883L don't work with the QMC 5883L. When you're buying a magnetometer online, there's a good chance that your HMC 5883L is actually a QMC 5883L. There are already a lot of tutorials online for the HMC 5883L. So in this video, I'm going to show you how to set up and program the QMC 5883L. The QMC 5883L has 5 pins: a VCC, ground, SCL, SDA, and D-ready pin. The sensor chip is on top of the board. Magnetometers and other directional sensors will have arrows on them like these. These show you the orientation of the sensor in relation to the PCB. This magnetometer detects magnetic fields in 3 axes. The x-axis points this way, the y-axis points this way, and the z-axis points up and down. Now let's set this up and see what the raw output looks like. The QMC 5883L uses I2C to communicate with the Arduino, so you only need 2 data wires and 2 power wires to connect it. VCC connects to 5 volts, ground connects to ground, the SCL pin connects to Arduino pin A5, and the SDA pin connects to Arduino pin A4. We're going to use a library to program the magnetometer. I found a pretty good one from SunFounder, which you can download from this link. Once you download and install that, we can take a look at the sketch. This program will output the raw values from each axis of the magnetometer to the serial monitor. Since the magnetometer uses I2C, we need to include the wire library. And we have to include the QMC 5883L library. Now we create an object so we can access the functions in the library. I'll call the object compass. It's a member of the QMC 5883L class. In the setup section, we initialize the I2C interface with wire.begin. We initialize the serial monitor with serial.begin. Then we initialize the compass object with the init function from the QMC 5883L class. In the loop section, all we have to do is declare a few int variables. The QMC 5883L outputs separate magnetism readings for each axis. So let's declare variables for each axis: x, y, and z. Now we need to get the readings from the sensor. The QMC 5883L library has a function called read that pulls in the values from the sensor. It takes 3 parameters. The first parameter is the variable that will store the reading from the sensor's x-axis. In this case, it's the x variable that we declared here. The second parameter is the variable that will store the reading from the sensor's y-axis. We declared a variable called y to hold the y-axis value, so that goes here. And the third parameter is the variable that will store the z-axis reading. We also declared a variable for the z-axis, so that goes here. Now we just need to print the variables to the serial monitor. So we serial print some text that says x equals, and then print the X variable. Then we do the same for the Y and Z variables. I've added a few spaces in front of the Y and Z text to make it easier to read on the serial monitor. At the end of the loop, we delay for 250 milliseconds to slow down the output a little bit. Now let's see what this looks like. So here's my magnetometer connected to my Arduino. I've attached it to a block of wood so it's easier to see the directional axes. The raw values you see here are the magnitudes of the magnetic field along each axis in microteslas. I have a magnet here. When I put the magnet in front of the x-axis, the x value decreases significantly. If I put the magnet in front of the y-axis, the y value decreases too. And if I put the magnet above the z-axis, the z value also decreases. But even without the magnet, the sensor is sensitive enough to detect the Earth's own magnetic field. If you rotate the sensor around the z-axis, the values for the x and y axes change. If you rotate the sensor around the y-axis, the values for the x and z axes change. If you rotate the sensor around the x-axis, the values for the z and y axes change. Alright, so that's the raw output. Now let's use these readings to get a compass heading. Magnetic fields are created by a variety of sources. An electric current flowing through a wire creates a magnetic field. But the magnetic field you're probably most familiar with is the one created by the Earth's iron core. This field surrounds the entire globe and allows humans to use compasses to navigate. The north and south you see on a map point to the Earth's axis of rotation. This is called true north and true south. They point directly to the north and south poles. But compasses naturally align themselves with the north and south poles of the Earth's magnetic field, not the poles of the Earth's rotation. Currently, the magnetic north pole is about 310 miles away from the true north pole. This means that the north we use for navigation is different from the north that a compass needle points to. The difference between these two directions is called the angle of magnetic declination. The angle of declination depends on your location on Earth. It can be up to 15 degrees off of true north. To relate the north reading of a compass to north on a map, you take the degree heading from your compass and add the angle of declination to it. I'll show you how to find your magnetic declination and add it to the sketch in a minute. But let's go through the sketch from the beginning first. This sketch takes the readings from each axis and outputs a compass heading in degrees. It also displays the cardinal directions, like northeast, southwest, or north-northwest. The sketch starts out the same way as the last example. We include the wire and QMC 5883L libraries. We create a compass object. We initialize the I2C interface, initialize the serial monitor, and initialize the magnetometer. In the loop section, we declare int variables for each axis, x, y, and z. Later in the sketch, we're going to convert the heading in degrees to cardinal directions. So we create a string object called cardinal to store that. Next, we get the readings from each axis with compass.read, and store the readings in the x, y, and z variables. To see how the x, y, and z readings are converted to a direction in degrees, let's take a look at a compass rose. In every compass, north is always referenced to 0 degrees. East is at 90 degrees, south is at 180 degrees, and west is at 270 degrees. If we point the x-axis of the sensor in the direction we want to travel, an angle is formed between 0 degrees north and the direction the x-axis is pointing. If we think of the sensor's x and y axes forming a circle like this, we can see that the north direction arrow has an x component and a y component. The x component is the output of the magnetometer's x-axis in microteslas, and the y component is the output of the magnetometer's y-axis in microteslas. The angle between the north direction and the x-axis of the sensor can be found with a trig function called atan2. This is the angle known as your heading. The atan2 function takes the magnitudes of the x and y sensor outputs and returns an angle in radians. I've declared a float variable called heading radians to store that value. To convert radians to degrees, we use the formula degrees equals radians times 180 divided by pi. The result will be stored in another float variable called heading degrees. Now we have the angle that the x-axis of the sensor is pointing in degrees relative to north at 0 degrees. Now we need to add our magnetic declination. To find the magnetic declination of your current location, visit magneticdeclination.com. I'm in San Diego, California, so I'll enter that here. The magnetic declination is right here. My magnetic declination is positive 11 degrees, 25 minutes. If your declination is negative, be sure to add the minus symbol when you put it in your sketch. The magnetic declination is provided in degrees and minutes. Minutes are just a fraction of a degree. There are 60 minutes in 1 degree. So what we can do here is divide 25 minutes by 60, and that will give us the fractional component. Then we can add that to the degree value. So my magnetic declination in degrees is 11.416. I'm going to copy this and paste it into the sketch right here. This is stored in a float variable called declination angle. On the next line, we take the heading degrees variable and use a compound addition operator to add the declination angle to it. Now at this point, we have a heading in degrees that has been adjusted for the magnetic declination. But there's one little quirk about the atan2 function. It only returns angles between 0 to 180 degrees and 0 to minus 180 degrees. In this situation, north is still 0 degrees, and east is still 90 degrees. But west is now minus 90 degrees instead of 270 degrees. And south is now positive 180 degrees, or minus 180 degrees. If the x-axis of the sensor is pointing southwest, the output of ATAN2 will be minus 135 degrees. But on a compass, this direction would be 225 degrees. So we need to convert the output of heading degrees to values between 0 and 360 degrees, just like they are on a compass. To do that, all we need to do is add 360 degrees to the heading, when the value is less than 0. You can see how adding 360 degrees to minus 135 degrees makes the angle 225 degrees, without changing its position. So at this point, the sensor will output an angle from 0 to 360 degrees, depending on where the x-axis is pointing. We do that with this if statement here. If heading degrees is less than 0, do a compound addition to add 360 degrees to the heading degrees variable. Having a heading in degrees is nice, but compasses usually also tell you the cardinal direction. Let's make this compass display the heading in degrees and the cardinal direction. To do that, we're going to divide up the compass into multiple ranges of degrees. So for example, when the x-axis of the magnetometer is pointing anywhere between 303.75 and 326.25 degrees, we'll print some text that says NW for northwest. And when the sensor is pointing anywhere between 101.25 and 123.75 degrees, we'll print some text that says east-southeast. We'll use a series of if and else if statements to display the correct cardinal direction when the heading is within that range of degrees. We start with an if statement that says if the heading in degrees is greater than 348.75 or the heading in degrees is less than 11.25, set cardinal equal to the letter N for north. Then we start the else if statements. If the heading in degrees is greater than 11.25 and less than 33.75, set cardinal equal to the letters N and E for north-northeast. We do the same thing for each cardinal direction. After we define the range of degrees for each cardinal direction, we print the results to the serial monitor. I'm printing some text that says heading, then printing the heading degrees variable. This will display the current heading of the sensor's x-axis in degrees. Then I print the value stored in the cardinal string. This will print the cardinal direction. I'm using a serial.print line, so the next time through the loop, everything will be printed to a new line. Then we add a delay of 250 milliseconds to slow down the output a little bit. Okay, let's upload this and see if it works. This time, I have the magnetometer's x-axis pointing up and the y-axis pointing to the left. So you can see the heading data being printed out. It's displaying the degrees and the cardinal direction. I have a regular compass here to compare the results. I'm going to align the x-axis of the sensor with the stationary arrow on the compass. I'm going to rotate the compass ring so that north is aligned with the tip of the red compass needle. The heading of the stationary arrow can be read off of the ring. It's about 290 degrees. And the output of the sensor is 290, 291 degrees. So the sensor is pretty accurate. As you can probably tell, this is a really useful sensor. If you have a remote-controlled vehicle, you could use the heading to control which direction the vehicle travels. or you could use it in a weather station to detect which direction the wind is blowing. In the next video, we're going to look at another type of directional sensor called an accelerometer.
The 3-in-1 Smart Car and IoT Learning Kit from SunFounder is a hands-on, all-included electronics kit that is perfect for anyone who wants to learn how to master the Arduino. The kit comes with an Arduino, 22 different sensors and modules, breadboards, jumper wires, and everything else you need to build a bunch of fun and interesting projects. Learn about robotics by building a remote-controlled smart car that can be controlled with an infrared remote controller, or drive on its own and avoid obstacles or fall on a line. Learn about the Internet of Things with a project that lets you monitor the temperature, humidity, and light level of a room from an app on your smartphone. And build a plant monitor that tracks the temperature, humidity, light intensity, and soil moisture, and displays it on your smartphone so you can keep your plants watered remotely. It's a super cool kit, and I had lots of fun building all the projects in it. So click the link in the description below to order the kit from SunFounder.